Welcome back everyone. In this lecture, we will see an application of sl2 representation theory in combinatorics. So, this work indeed suggested by Richard Stanley. So, he demonstrated the power of algebraic techniques that can be actually used to get some interesting results in the representation in combinatorics. So, towards that actually so we will actually see one example and then I will demonstrate how one can use sl2 representation theory to get some applications in combinatorics. So, the problem that we are interested in, we want to actually prove some unimodality of some interesting numbers that naturally appears in combinatorics. So, the problem that we are going to address today is counting the number of unlabeled isomorphic graphs of n vertices and k edges. So, basically we start with something called simple graphs. Okay. So, finite simple graphs. So, what does it mean? That means it has no loops and no multiple edges. Okay. So, we only count whether there is an edge between given two vertices or not. Okay. So, let us always take the indexing of the vertex set is to be 1 to n. So, this we will keep it as vertex set. For example, when n equal to 2, so we have two vertices, either there is an edge between 1 and 2 or there is no edge. So, only two graphs are possible. So, if we take n equal to 3, then we have three vertices. So, there will not be any edge between them and then we can put one edge between two vertices, but the choice of that pair of vertices does not matter because we want to actually talk about unlabeled graphs. So, that means we do not care about actually the labeling of the vertices. So, if you count these unlabeled graphs up to isomorphism with n vertices and given k number of edges, that is the number that we are interested in. So, if we take n equal to 3 with 0 edge, there is only one graph, with 1 edge there is only one graph, and if we take 2 edge, again there is only one graph, and with the 3 edge there is only one graph. Okay. So, the choice of vertices do not matter in the unlabeled graph. So, let us denote G n k by the number of, okay, of course, non-isomorphic unlabeled graphs with n vertices and k edges. Okay. So, this is of course, we are counting always modulo the isomorphism. So, we are going to only consider simple graphs, simple finite graphs. Okay. So, what we are going to claim? So, the claim is these numbers are very interesting, they appear in many places. For fixed n, this sequence G and K, where K runs over from 0 to whatever that n max, it is indeed unimodal. Okay. One can easily see that when n grows really very big, then these numbers actually grows really very big. So, we do not have any indeed computationally they are very difficult to compute, but one can make such very nice statements about these numbers without even computing them. So, that is the power of these algebraic techniques. So, how one can approach this problem? Okay, so to approach this problem, first what we will do, we will actually consider labeled graphs, and then we take the vector space spanned by these label graphs. Okay. So, then we can make the symmetric group act on that. So, then that action actually leaves, for example, unlabeled graphs. Okay. So, then we can actually define SL2 action on this the subspace, which is actually kind of our sub representation, which is spanned by this unlabeled graph. So, using that, one can actually try to prove these numbers indeed symmetric about the origin. Okay. So, we are going to very explicitly construct SL2 action on some important subspaces of this n labeled graphs, and then we will use SL2 representation theory to prove this result. So, let us see how one can do this step by step. So, I am only going to outline the proof, because the computations are very simple. Okay, one has to just simply sit and do the computation, which I will leave it to you to check. So, let us start with this Wn. Okay. So, before that, let's call this Gn. So, Gn, this is the set of all, let us say, labeled graphs on vertices 1 to n, the set of all labeled graphs, okay, on the set of vertices one to n. So, we will use 1 to n for the vertices. Okay. So, then you can take this Wn, so which is going to be the direct sum of C span of all these graphs, where G comes from your Gn. Okay. So, then so naturally the symmetric group act on this. Okay. So, we have the symmetric group Sn act on Wn. So, by just permuting the vertices. Okay. So, by permuting the labels of a labeled graph. Okay. So, now we can also consider this subspace Wnk, which is sitting inside Wn. Okay. So, what is this? This is the subspace spanned by all G in Gn, such that G has exactly k edges. So, this is the subspace spanned by all G in Gn, such that G has exactly k edges. Okay. So, now this symmetric group is acting on Wn, and it also acts on this Wnk. Okay. So, now if you think about it, it is a simple exercise that if we take the number G and k, so that is nothing but the dimension of this fixed point subspace. Okay. So, we can look at all possible Sn invariant elements inside W and k, then the dimension of that space is going to be exactly G and k. So, this is something very easy to see. I will leave it as exercise. So, this W and k is a Sn sub representation of Wn. Okay. So, that is something again easy to see. So, Wnk is Sn sub representation of Wn. So, in particularly we can talk about fixed point elements inside that sub representation. So, given any representation, okay, let us say G, group G acts on a representation capital V, then the fixed point subspace will be those vectors in capital V such that GV equal to V for all G in G. Okay, this is called the fixed point subspace. For example, all these things naturally appears in the orbit stabilizer theorem and so on. Okay, so we have this natural identification. So now, how are we going to use this information to say something about G and K? Okay, so this is where we need to actually define sl2 action on Wn. So we define sl2 action on Wn. Okay, and of course we can restrict that action to Wnk, and then we can look at what happens. So this sl2 action that we are going to define, it will naturally commute with Sn. Okay, so we want to define such that this action of sl2 on Wn commutes with the action of Sn. Okay. So that is why one will be able to actually restrict the action. So let us first actually take two indices I and j from 1 to n. Okay. So then, so basically given two vertices, so we are going to look at those vertices in a given graph G. So then there are only two possibilities, either there will be an edge between those two vertices or there may not be any edge between those two vertices. Okay. So depending upon that, we are going to actually define some operator. So we define the following operators. So we call them Aij and Bij. So Aij is some operator that is actually takes the graph G, and whenever there is no edge between I and j, it just adds up Ij. Okay. So Aij is defined from Wn to Wn. So what it does, it takes G and then sends it to G union Ij if Ij is not an edge. Okay, this is the edge set of G. So when there is no edge between Ij, you just add that Ij edge. So then you can actually get a new graph which will have more edges than G. Okay, exactly one more edge. Otherwise, you send it to 0. Okay. And how you define this Bij? Again, Bij is also naturally defined. So you take some graph G, and if there is an edge between Ij, you just delete it. Okay. So that is how the Bij is defined. So you just take G and then the delete this edge Ij if Ij is on edge in the given graph. Otherwise, you just send it to 0. Okay. So basically, Aij includes this new edge between Ij, and Bij just deletes if there is edge between Ij. So these are all the two operators that we are interested in. Now, if you actually think about it, so whenever you have the tuple St which is different from, let us say, uv, again those are all vertices. So then we can consider this Ast Buv, these two operators. So if you actually take this ST which is different from UV, then you can easily see that these operators AST and BUV, they actually commute. Okay. So, as an operators they must commute, because these vertices ST and UV, they are different. In particularly the corresponding edges will be different. Okay. So, AST just adds whenever there is no edge between ST, and BUV just deletes whenever there is an edge between UV. So, I will just leave it to you to check this. This is something very easy to check. Now, we can actually compute what will happen between the commutator AST BST when you apply it on G. If you compute it AST comma BST, the commutator on any given graph G, then you can prove that it is going to give exactly G if ST is an H. Otherwise, it is going to give minus G. So, it is not going to change it too much. Whenever ST is an edge, it is going to give you G, otherwise it is going to give minus G. So, these two things are very easy computations. I will leave it to you. Now, using these operators Aij, Bij, one can actually define all the operators that we are interested in. Okay. So, recall, to define a representation from SL to C to any GL of any vector space V, you need to specify how the basis elements of SL2 act. So, they are like X, H and Y, how they act we have to say. So, if you are interested in actually defining this representation on GL of Wn, so we have to say how one can actually define these representations. So, we have already noticed, so recall X, H, Y, so it is the basis of SL2 and they satisfies these commutator relations. In particularly bracket xy must be always H, okay, and Hx is nothing but 2x and Hy is minus 2y. Now, using this relation one can easily see that to define H, it is enough to define x and y. As an algebra, SL2 is generated by x and y. So, it is enough to define what is x and what is y. So, that is what we are going to do. So, we are going to define what is this xwn and then what is this ywn, and then one can extend it, not a problem. Okay. So, basically the commutator of that is going to be hwn. So, we are going to define that as follows. You take xwn to be sum over all aij where I less than j. Similarly, what will be ywn? That is going to be sum over all bij where I less than j. Okay. So, now it is immediate that, okay. So, I will leave it to check, verify that if you compute the commutator xwn and ywn on any g, okay, where let us say g indeed comes from wnk, where it has exactly k vertices, sorry, k edges. So, then if you compute this commutator, then you can see that this is going to give you exactly the eigenvalue 2k minus n choose 2 times g. Okay. So, that means this commutator indeed acts diagonally on Wn. On exactly Wnk, it acts with the eigenvalue 2k minus n choose 2. Okay. So, that is something very important property of SL2 action on any finite dimensional representation. H should act diagonally. Okay. So, now to say that this is exactly giving us representation of SL2. So, we have to verify the following formulas. So, I will leave it to you to verify. So, this is the first thing to verify. The second thing is when you define HWN to be the bracket XWN and YWN, then you have to verify that HWN comma XWN. So, this you can take it as a definition. This is going to be going to give us twice XWN, and similarly HWN YWN should give us minus twice minus 2 YWN. Okay. So, if you check all these three formulas, then we have SL2 representation of SL2 action on this WN. Okay. So, these are all routine checkup. So, I will leave it to you to check. So, now we have the action of SL2 on WN. So, now you can see that this action is indeed actually like, because everything is defined using this Aij and Bij, it is easy to see that Aij, Bij they commute with the action of Sn. Okay. So, because these operators x and y, they are defined using this sum of Aij and sum of Bij. So, you can also see that the both operators naturally commute with the action of Sn, and similarly Hn also commute with the action of Sn. So, in particularly SL2 action on Wn commutes with Sn action. Now, what we can do, we can actually look at what happens to Wnk. Okay. So, note that this Wnk, so that is again Sn submodule. Okay. So, now if we take this SL2 action, okay, because it commits with the Sn action. So, you can also see that from this immediately there is this SL2 action on this fixed point subspace WNSN, which is indeed decomposes as WNKSN, where k runs over 0 to n. Okay. So, SL2 action on Wn commutes with Sn action. So, this implies there is a natural action on natural SL2 action on this space WNSN. So, in particularly we have this SL2 action on WNSN. Okay. So, SL2 action on WNSN. Now, what about H, how H acts? So, H acts diagnostically, because that is a computation that we did on Wnk itself. Okay. If we take Wnk, you can see that for any g, it is giving us so the action of this commutator is giving us this 2k minus n choose 2 g, k is fixed. So, it is basically Wnk is the weight space corresponding to 2k minus n choose 2. So, if we look at this H action, okay, so the H action has the weights 2k minus n choose 2. So, H not only acts diagonally with the weights 2k minus n choose 2 for k greater than or equal to 0. So, this is immediate thing. What is the weight space corresponding to this weight 2k minus n choose 2? Okay. So, we are actually looking at this action, okay, SL2 action on WNSN. Same formula works, so that you can see that H is also acting as diagonally on this Wn power Sn with these weights. Now, what is the weight space? Now, the weight space, of course, corresponding to the weight 2k minus n choose 2. So, this is going to be exactly WNKSN. Okay. So, these are all the weight spaces for us, because the same formula that we calculated is going to tell us this. So, these are all the weight spaces. So, those are all the Vk that we are interested in, but we know that the dimension of this WNKSN, so this is nothing but just GNK. Okay. And you can see that all these weights, okay, if we take these weights, so these are all 2k minus n choose 2. So, these all have same parity, okay, they have same parity as n choose 2. Okay. That means they are all either odd or they are all either even. But we have the inequality that actually tells the dimension of V naught is greater than or equal to dimension V2 and so on. Similarly, dimension of V1 is greater than or equal to dimension of V3 and so on. But here, since all the weights are either even or odd, so that implies immediately that these numbers must be symmetric at 0 and unimodal. Okay. So, one can immediately see as a corollary of our previous results that G and K is unimodal and symmetric about 0, symmetric about 0 or the origin. Okay. That is because all the weights of this module that we have constructed, so that is indeed all of them have same parity as n minus n choose 2. Okay. So, like this one can actually use SL2 representation wherever we have the SL2 action. So, we can actually use this action to say something more about the weight spaces and the behavior of the weight multiplicities. Okay. So, I hope you will be able to work out all the details of this example. Okay. So, similar to this maybe one can find many examples in the literature. Okay. This is indeed very nice approach to prove if for some reason if you know that you have a sequence which is unimodal and symmetric about the origin, then maybe like there is natural SL2 action on that. One can actually look for that and then try to prove that because of that action it is actually becoming unimodal and symmetric about origin. Okay, I will stop here. We will actually continue with some examples of representations in the next class. So, maybe we will see actually how to construct some new representations from the old ones. Okay, thank you. We will see next time.